Good morning, everyone. Today I am going to present electrical and mechanical transfer function models, which is a part of control systems and R 2021 regulation. In this presentation, we will understand how control systems are represented mathematically and how mechanical systems are modeled using basic physical elements. Mathematical model of control systems. A control system can be represented using a set of mathematical equations, which is known as a mathematical model. These models helps us to analyze, predict, and design control systems effectively. Without mathematical models, it becomes difficult to study system behavior accurately. Types of mathematical models. There are three main types of mathematical models used in control systems. Number one, differential equation model, transfer function model, state space model. In this unit, we mainly focus on differential equation models and transfer function models. Differential equation model. The differential equation model is a time domain representation of a control system. It describes the relationship between input and output using derivatives with respect to time. This model is commonly used when analyzing system behavior directly in the time domain analysis. Transfer function model. The transfer function model is an S domain representation of the system. It is obtained by applying the Laplace transform to the differential equations, assuming zero initial conditions. Transfer function makes system analysis easier for stability and frequency response studies. Modeling of mechanical systems. Mechanical systems can be classified based on the type of motion into translational mechanical systems, rotational mechanical systems. Each system is modeled using basic physical elements such as energy storing and energy dissipating components. Translational mechanical systems. Translational mechanical systems move in a straight line. They consist of three basic elements: mass, spring, dashpot, or damper. These elements are used to represent real-time mechanical behavior mathematically. Mass element. It is an element that stores kinetic energy. When a force is applied to a mass m, it produces an opposing force proportional to the acceleration of the body. Here we assume that elasticity and friction are negligible. The force is applied to a mass denoted as Fm is directly proportional to the acceleration. Acceleration is denoted as A. So Fm is directly proportional to A. F is equal to constant term m d square x divided by dt square. Elasticity and frictions are negligible. Spring element. Spring stores potential energy. When a force is applied to a spring with stiffness K, it produces an opposing force proportional to the displacement. In this case, mass and frictional effects are neglected. Friction force of spring is denoted as Fk is directly proportional to the uh, displacement x. Displacement is denoted as x. Next, dashpot element. A dashpot or damper represents frictional effects. The opposing force produced by a dashpot is proportional to the velocity of motion. Here we assume that mass and elasticity are negligible. Dashpot of force is denoted as Fb is directly proportional to the velocity. So Fb directly proportional to v. Next, modeling of rotational mechanical systems. Rotational mechanical systems move about a fixed axis. They consist of three basic elements: moment of inertia, torsional spring, dashpot. These elements help in modeling rotational motion mathematically. Moment of inertia. Moment of inertia represents resistance to angular acceleration. When a torque is applied, it is opposed by torques due to inertia, elasticity, and friction. According to Newton's law, the algebraic sum of all torques is zero in equilibrium conditions. Torsional spring. Torsional spring stores potential energy in rotational systems. The opposing torque is proportional to the angular displacement. Here, moment of inertia and friction are assumed negligible. So, Tk directly proportional to theta. Dashpot. A rotational dashpot provides a rotational friction. The opposing torque is proportional to the angular velocity of the system. In this model, inertia and elastic effects are neglected. To conclude, we studied the mathematical modeling of control systems, understood transfer function representation, and learned how translational and rotational mechanical systems are modeled using basic elements. Thank you.